Hi, we are Team ME39 working on a masking method for airfoil cooling air measurement with Pratt & Whitney. Our team members are Calvin Colby, Andrew Dolan, Sammy Yanyan, and Tianfeng Liu. So for our problem statement, Pratt & Whitney must test the interior airflow distribution of their turbine blades. So they'll put the blade into the test rig and then cooling air is flowed in through the root, through the interior cooling channels, and out through the cooling holes. And so they'll block all but one row of holes, flow the air, check that the airflow requirements are being met for that specific row of holes, and then repeat for each row. To accomplish the blocking, Pratt & Whitney currently uses a wax and tape method, which is very time consuming, very messy, difficult to apply, and requires washing afterwards. And so all in all, it ends up taking about 2 hours to apply, test, and remove. So that brings us to our objective. Our goal is to develop an alternative method for blocking cooling holes that reduces application, testing, and removal time to about 20 minutes, which will create millions of dollars in time savings for Pratt & Whitney. Our deliverable is to fabricate this blocking mechanism to block specific rows of holes on a PW2000 turbine blade. So you can see with the figure on the right here, this is not a P&W turbine blade, so it's not exact, but we're flowing these holes circled in blue and blocking all the other holes. And so there are some design restrictions we had to consider. Our project is really a proof of concept showing that our design works on this specific row of holes that are circled. But our design must be able to be adapted to other rows of holes and to other blades, so there can't be anything hyper-specific to this blade in our design. Additionally, the blocking mechanism should be durable and easily applied and removed in the same exact way every single time. Our design must withstand about 8 psi of pressure in the holes that we're trying to block, and must have 0 leaks in the blocked holes as well.
Okay, so the first design we created is the hard shell design. In this design, we have a hard outer layer shell and a softer inner layer. The hard outer shell is made out of Vero White Plus. It is a rigid and durable general purpose high resolution opaque white material. The inner layer is made out of blue silicone mold. It is a soft, strong rubber which are tear resistant and exhibit low long-term shrinkage. It also has a good bounce back when applied with pressure. So after pressure is applied, it goes back to the original state better than most other materials. In this design, both the inner and outer layers are attached to one another. So we also split the cube into two pieces where we made a zigzag cut down the middle shown in the design. We changed it from a smooth straight cut to a zigzag to ensure that the piece do not slide off easy from the blade. With this two-piece design, we can also attach and detach the pieces from the turbine blade more easier. Okay, so for this box and plunger design, it is similar to the concept of the hard shell design where there is an outer hard shell and a softer inner layer. The hard shell is also made out of Vero White Plus, and the softer inner shell is made out of blue silicone mold as well. However, with this design, the outside hard shell is separate from the inside softer layer. There's also a plunger on the side where, when applied with outside force, the plunger applies pressure to the inside softer layer. So by adding the plunger, we're able to change the distance of the plunger, where we can determine how much pressure to put to keep the inner layer still. In this design, while the outside shell is a box, the inside layer is a two-piece design. So we can again attach and detach the pieces from the turbine blade much easier.
Throughout the past year, we have created several iterations of each of these blocking method designs. Using a 3D printer, we were able to create models quickly and inexpensively. This allowed us to continually test the feasibility of our designs. While testing our early designs, we encountered issues with durability. We researched the durometer of various sealing materials in order to find a more durable material. This ultimately led us to using Pratt & Whitney's proprietary blue sealing material for our final iteration. With this durometer increase, the box and plunger design did not perform as expected. The sealing material was too stiff and the plungers were unable to press firmly against the blade in order to achieve proper sealing. After conducting the airflow testing, we received the best cooling hole sealing results when using the hard shell design. The hard plastic shell improved the structural integrity of the model, which reduced leakage. A two-piece design allowed for the easiest application due to the shape of the turbine blade. This two-piece hard shell design resulted in a significant reduction in manufacturing cost.